All right, so I'm going to do this one with you. So what is it? So basically, this is practice exam question number 1. This is practice exam number 2. Let me get this straight here. What is? Come on. This is practice exam number 2, question 1. And basically, what it says. Let me just write the key facts. Carly, it's an $18 cake. $18 cake. Here's what Carly thinks. Carly, what? What does it say about Carly? Carly thought strawberry banana equal strawberry and banana equal and what? Chocolate twice of strawberry or banana, right? Chocolate twice as much as either strawberry or banana. Right. And what does Dale think? Dale has different feelings. Dale says chocolate 3 times strawberry. Chocolate 3 times strawberry. Strawberry. Dale, chocolate 3 times strawberry. Further, strawberry twice banana. Strawberry twice banana. Okay. All right, there's the facts. And then they give some kind of thing. Carly's eyes. Okay, so then we got this cake, which is chocolate. And what's that? Strawberry and banana. Here, let me make it a little bigger. All right, so. Chocolate, strawberry, banana. Okay, there's the key facts, right? The key facts from the question. So let's do Carly first. Let's do the facts on Carly. So let's just what you need is basically a cake according to Carly's value system, and a cake according to Dale's value system, and those will be different. In fact, maybe I should space it out a little bit better and separate it. Yeah, maybe that would be a good idea. So, let me do that. So, yeah, I'm going to erase, well, I don't want to erase everything. Yeah, it's just, I guess I'm going to. All right, so I'm just going to write it. I'll try to make it organized. So, so again, it's an $18 cake. Okay, and I'll put Carly over here in left. Carly, what is again about her? Strawberry, strawberry equal to banana, chocolate times 2. How about that? So there's Carly. On the other side, over here, I'm going to do Dale. And Dale, what does it say about Dale? Chocolate 3 times strawberry. 3 times strawberry. And what else? Strawberry twice banana. 2 times banana, yeah. And so I'll have a whole cake for him, which is the same cake, but he just sees it different, you know, putting on his glasses. All right. All right, so everybody with me first off. So you got to, you know, different people see things differently. These are the hardest ones by far. Well, these and the sealed bids. The cake ones and the sealed bids, hardest thing probably almost all semester. Probably right. If you can get this down, you get an A in this next test. This is the hardest thing on, probably in the whole course, for sure on the next test, is the cake ones and the sealed bid ones. These are the hardest. The rest is a lot easier than this, you know. So, all right, so let's get this down. I know this is the tricky part for people. So, whenever they have cakes and pies and that kind of thing, and they're listing out their values, you got to have a whole cake thing for each of them because they see it different. So here we go first off with Carly. What do you do? Remember that one we did a couple days ago where somebody liked something twice as much or 3 times as much? Remember you put X and 2X and 3X and things like that? That's what we're going to do here also. So what does it say, Carly? Strawberry and banana are equal. Chocolate is 2 times. Okay. So that means I'm going to come down here and I'm going to go strawberry is X, banana is X, chocolate is 2X. Almost. It's almost right. It's technically wrong. but it's close. Close to, let's just start with that thinking. Is that good so far? Quez, you're here. You were here when I left, huh? All right. Anyway, so we're good so far. Right? That makes sense, right? They're just saying chocolate is twice, strawberry and banana are equal. So these are both X. I'm going to add them all up in a minute to be 18. But hold on. Here's the problem. When somebody says they like chocolate twice as much as whatever, strawberry or whatever, they mean they like the flavor of chocolate, right? Twice as much as they like strawberry. So if you also give them twice as much of it, they're going to like that 4 times as much. Did that make any sense? No. So you can like the flavor twice as much, and you can be handed twice as much. Do you see the chocolate part's going to be 4x? Because not only do they like the flavor twice as much, it's twice as big as the strawberry or the banana. So really you should get a 4x. Double for the taste, double for the size.
It's how people value that item.
Yeah. First off, they just value. Now, the way to make this easier, because that's pretty tricky, just do this. Just make them all the same size. Honestly, I'm not going to give you one on the real exam where they're not all the same size. That's just a little bit too tricky. We didn't have any like that in homework. So here's what I'm saying. But if you can do this, no, I will give you one like that, for example, where they're all the same size. So do that first off, just to make life easier. Just shoot a line up the middle. Now they're all the same size. We don't have to double think and all that stuff. They're all the same size. Good? Now you can just say, hey, chocolate's twice, so this is 2x and this is 2x. There's the 4x thing I'm talking about, but whatever, good enough, right? The chocolates are twice, because that's what they said. They like chocolate twice as much. Good? Now, all those add up to equal 18 bucks, right? So I just go to a little algebra equation here. 2x plus x is 18. The whole cake is worth 18 bucks it's worth 18 bucks to everybody. Right? That good? So for Carly, just add them all up. 2x, x and x is 18. Everybody see what I'm doing there? Okay? Like terms from algebra. These have understood ones in front of them, huh? So 1, 2, 3, 4, 5, 6x is 18. Good so far? How do you solve for x? Divide by the 6. X is 3. So x is 3 bucks. So then you just go back in here and you just go, okay, so I got that. So that means this x here is $3 for the banana part, $3 for the strawberry. And these are each 2x, so this would be 6 bucks, right? And 6 bucks. So the whole chocolate half is 12 bucks to Carly. Does that make sense what they did there? Right? So everybody see, I just said, hey, strawberry and banana are equal XX. Chocolate's twice, but you got to make the chocolate sizes the same. So 2x, that's twice. Add them all up to be the $18 cake. 6x is 18, x is 3. That means x is 3. Everywhere you find x, it's 3. X is 3. And double x is 6. Double x is 6, right? And so the cake is 6, 6, 3, 3. If you add that up, it's 18, right? 6, 6 is 12, 15, 18. That's right. So that's how Carly feels about the cake. Now we're ready to answer any questions about Carly and the cake. What did it say? I'll put it back here. Yeah, Carly. Let's just do them all. This will be part of our practice exam work. Yeah, so Carly, in Carly's eyes, the strawberry quarter, this little strawberry quarter, let's go back. The strawberry quarter, meaning, come on, this section is worth what to Carly? $3. $3 to Carly. What option was that? I see there's 13 clicks. All right, you guys are clicking in. It's obviously C. So the answer, everybody got C? I'm going to close her down. Click C. All C's are in. We all in there? 4, 5, 6, 7, 8, 9, 10. I'm down. 18. All in. Last call. Everybody got C. If you click something earlier, just go ahead and click C now. It takes the last click. So click C. If you'd click something earlier, it'll take your last click. Everybody good? Going. 5, 4, 3, 2, 1, done. Good. 100% of you said C. Good. Let me save it, and then we'll do parts. Here, in fact, you try now. Go while I'm saving this. Go ahead and go on with like 2 and 3. So if you can do 2 and 3 there. It's on the practice exam anyway. We're kind of getting to jump on the practice exam. So try 2 and 3. I'll save this stuff. We're still talking about Carly, right? Oh no, Dale. Switches to Dale. Oh, I didn't do Dale. It's already switching to Dale. Well, we got to switch to Dale. You can do Dale. Well, Dale's a little tricky. See if you can do Dale. You need a whole different cake for Dale. He has a different value system, right? So really you need to go back over to this and finish Dale. So finish the Dale cake now. Let me give you a hint. Start with the lowest one. Break the middle again. Break the middle. You know, you need to break that. You need to break that chocolate so it's same size. Again, I'm not going to be that tricky on the real test. I'll make them all the same size. So chocolate. So do that first off because you want them all the same size. You don't want to be messing around with different sizes. Now, let me give you this hint. Start with the lowest valued one in Dale's eyes and work your way. That's X. And then work your way up from there. Do you know what I mean? Which one does Dale value least? What's his least favorite flavor? Banana. Start with banana and pop an X in there. Right? Banana is X. And then build it up from there. That was quiz 7 for us. And today's the last day of May and it's raining. Will it rain in June? All right, we good? We getting that? So banana is X, and then he likes strawberry twice as much as banana. So strawberry is 2X. Now chocolate is 3 times strawberry.
So 6X.
6X and 6X. Because it's 3 times the 2X. 3 times the strawberry. Does everybody see that? That's why it's easiest to start with the least. So the lowest is banana, double that for strawberry, and then triple that for each of the chocolates, because that's what it says, huh? So it's easiest to start with the lowest when they have like 3 statements in a row, you know? 2 statements, 3 things, right? Does that make sense? So now we can go in, and then add those up. Remember, add them all up to be $18. The cake's $18. So add all those up, right? 6X, 6X, 2X, and X adds up to $18. What is that? 12, 13, 40. And that's 1. 15X?
Yeah.
Is 18 divided by 15. X is, what is that? 1.2. 1.2, thank you. $1.20, in other words. X is $1.20. 1.2, use your calculator. So that means go back now and just pop that in. So X right here, this is $1.20 for banana. Double that for strawberry. It'd be $2.40 for strawberry. Double. And then 6 times that for each of the chocolates, which is $7.20, right? I believe. Use your calculator.
Yes.
And I'm like the human calculator, right? I'm ready to take on. You guys know who the fastest human calculator in the world is? Do you know that? Who the fastest human calculator in the world is? I saw this person at a conference. Better keep this quick. We don't have time for long stories. Real quick. I saw a conference. Saw this person 12 years ago. Big math conference, Monterey. 300 math teachers, some kind of big math conference. Something you would love to go to. I'm just kidding. All right. So we all gathered there, big math conference. They featured the world record holder, fastest in the world, not just local or something, right? The Guinness Book, world record holder. This person still is. Fastest human calculator in the world. And there was nothing about what the person looked like. And what cracked me up was my stereotypes. I don't know if you're like me, but I was wondering, what would this person look like, right? And I pictured, we got the big stage, big hotel in Monterey, and I pictured, the curtains would open and out would pop this, 14, 15-year-old, skinny little Indian or Asian boy or girl that would say, hello, I'm the fastest human. That's just what I pictured. Curtain, the fastest in the world, right? Curtains open up, out pops this 32-year-old white guy. Could be your neighbor with sweats on. Just American. Total regular Joe. And he's Mr. Casual. Just comes out, hey guys. I'm thinking, what, you? You are the fastest. And he is. He's still talking to Google. He's like 50-something. He's my age. He's like 50-something. And he's the fastest in the world. I said, he doesn't have a college degree. Ever since 4th grade, he could just erase the TI calculator on the big screen and he used instantaneous. Anyway, enough of the stories. It was just funny to me, my stereotypes. He's an American. He's the fastest in the world. All right, so there we go. So 720. So you could double check. Add those up. You should add to 18, right? 720, 722, 40, 120, the whole cake, $18, right? So now we can answer any questions. Is that good? Everybody got that down? I'll flash back to the questions now, if that's okay, if you got that copy down while I was telling that story. Back to the Elmo questions. All right, in Dale's eyes, the chocolate half. So what's the chocolate half worth?
14.
Yeah, the 720 and the 720, whatever that is, 1440. Yeah, the D. Everybody see how we're getting at? The two 720s? Add it up. Is that okay? Two 720s. Okay, and then in Dale's eyes, the piece shown below. Now, what's that? How are you going to do that weird little piece? Everybody got it? I'll flash back to the thing and I'll do it for you. Notice it's just half the strawberry, half the other. Just take half of each of them. See that? Let me go back. I'll show you. It's 45 degrees. That's half of 90, right? 90 is the right angle. 45 is half. So they're basically just saying, look, take half of the strawberry and take half of the banana and put them together. So just take half of the 240 and half of the 120 and add them up.
Well, it's essentially, because 60 cents plus 60 cents is $1.20. Oh, 240, sorry.
Yeah, so half of 240. So 120 and 60, 180, right? So it's half of the 240 and half of the 120. So that comes out 120 and 60, so 180 for that little weird piece on number 3. I'm answering question 3 on the practice exam right there. 180. Does that make sense? How I did that? Because they're just taking half of the strawberry's 240, so half of that, half of the banana's 120, half of that 60. Add them up, 180. That little chunk must be 180 to Dale. That's how Dale sees it. It's worth that, $1.80. Right? We'll go back to the question again. Right? See the 45? That means half of 90. That's all that means. Right? That good? What if they made it like 30 degrees? Each of those 30. 30 is what portion of 90? It's a third. Right? So just whatever portion they give you of the 90. Right? You with me? You get that? Is that okay? Right? Because I keep going back and forth. So let's go back to this, right? So the, right, because the strawberry and banana, those are 90-degree sections. So if they give you some weird angle, like 40 degrees, just take 40 over 90 times the whole thing's value. Does that make sense? If they gave me 40 degrees, I would go 40 over 90. You don't need to put degrees. Times, like they did the strawberry section, I'd go times 240. Because you're getting 40/90ths of the $2.40 section, for example. Does that make sense? Right? Whatever angle they give you, you're taking that part of the whole. The whole is 90. The whole angle. So they give you 40-degree angle. So 45, I didn't even mess with it. If they gave me 45, I know 45 over 90 is a half. That's why I did a half, right? So it's just half of 240 and half of 120. Add them up. Okay, I think, let's go back to the thing. I think you've got it. I think they actually had a couple more. This one went on and on and on. Yeah, here's number 4. So we're basically doing our practice exam right now. Here's number 4. Same cake. Carly's the divider. Which of the divisions would be consistent with Carly's value system? So I'm going to go back to Carly. I'll be drawing it over here. So look at what you got for the Carly cake. This is question 4 on practice exam number 2. Chocolate, strawberry, banana, right? And how does Carly feel? Let me go back over here to the thing. What was Carly's feelings again? I already forgot. XX, 2x, 2x. Okay, so x, 2x, and we already found out. What were the numbers on that? 6, 6, 3, 3. Okay, so we already found out that it was $3, $6, $6. So this is Carly. Question number 4 on practice exam 2. There it is. And they're saying, how will Carly cut it if she's the divider? if she's the divider? Well, what does that mean to be the divider? What does the divider always do? That's the first thing you gotta have clear.
Saves them all equal.
The divider will cut it equal because they get last pick, right? The cutter gets last pick. That's the main thing you gotta remember. So the cutter will cut it fair in their eyes because they know they get the last pick, right? So they will cut it fair. So the question really is asking, which of those three cuts is fair in Carly's eyes? Let me draw out the three options. So there's number one here. And then there's number two. Some kind of thing like this. This is 135 degrees. And then there's the other one. Whoops. All right, I'm trying to do this here and not doing so well. Okay, so which of those three will, so here's division 1, division 1, division 2, division 3, right? Which of those three will Carly do? Let's look at number 1. Number 1, this would be $3, $3, and this is $12, right? Because 6 and 6. Will Carly do that? Will Carly do division 1? Will she cut it right through the middle? She would think this is worth $12, this is worth $6. Go ahead, Dale, which one you want? No way. She'd be scared to death Dale would take that one. They're not equal in her eyes. See the deal? She will not do division number 1. Because they're not equal in her eyes. It's 12 and 6. She won't cut it there. Remember? Because the cutter will cut them equal in their eyes. That way they don't have to worry about which getting the last pick. Right? So it's not number 1. Number 2 looks kind of tricky. Let's go on to number 3. We'll come back to 2, because 2 is the answer. Number 3. Why will she not cut number 3? Well, we already know this is worth, look at the chart here, $6. This is worth 6, 3, and 3. In other words, what was that? 12. $12. So the bottom part's 12, that's 6. No, she won't do that. They wouldn't be equal. So it's got to be division 2. Is it? Is that really equal? It is. Let's prove it. This part's worth 3, right? Just grabbing the 3 there. This part right here is worth 3. And if I can break the chocolate, the 135 is just 90 and 45. It's just straight up and then half, right? Straight up, this is worth 6. And then this section is worth $6. It's broken into 3 and 3, isn't it? See how that's $9, $9? Right? 9, 9. Yes, that's what Carly will do. Those are equal value to Carly. And then she doesn't care what Dale picks. She's okay with getting last pick. They're equal value to Carly. You see how I figured out the 3, 3, right? Because this is just splitting this 6, just cutting this right in the middle, so 3, 3. Right? 3, 3, that's the 6, 6, 3, 3. Right? Everybody good with all that? That's probably the trickiest question on the test. So she'll do division number 2, won't she? That's what the cutter would do. So it's fair in the cutter's eyes. Remember, the cutter always cuts it fair in their eyes because they get last pick. So going back to the question then, well, yeah, it's division 2. We're done. Good. That's it. That's it for that. All right. Let's move on. We have to cover. Well, actually, I need to tell you one other thing. Remember yesterday we did the. What did we do? We did. Yeah. So standard divisor. Let's do that. Let's talk about that. So standard divisor. It was what? Was it? What was it? Total population by number of seats, right?
Yeah.
Total population divided by. So put that in your 3x5 card, even for today's practice test, right? Standard divisor is total population over number of seats. Okay. So what's the total population? Now they're not giving me the total, are they? How can I get it? Just add them up, right? Just total. Guess what it's going to be? It's going to be 100 because those are percentages. But it's okay if you don't notice that. Just add them up. It is 100. That's 100%. So total population is 100. They're just giving me percentages, which is fine. Over how many seats? 500 seats. Right? 500 seats. That's 0.2. That's what they want. 0.2. .20, 0.2, same thing. Good there? Standard divisor. Find the standard. Now, what's a standard quota? Well, that's the standard quota. That's when you just take each number and you divide. So for A, standard quota for A is A's number, 6.89, over the divisor. That's why we call it the divisor. You use it to divide all the other numbers with. Divide by 0.2, you'll get 34.45, I assume. Is that right? Yeah, that's exactly right. Okay, good. And so B, C, and D are all the same. And that's all for that question. Is it okay if I flash off that one? Is that okay? Remember all that? Just standard divisors, population over seats, and then each of the other standard quotas, you divide by the divisor. That's called the standard quota, so I hope the language does, because on the practice test today and the real test tomorrow, they'll ask you, what's the standard quota? Then they'll say, what's the final quota? That's different, right? Standard quota is just that first number when you divide. That's what they should get in all fairness. But the problem was, the whole chapter was about, you can't have a part of a representative. You can't give them 34.45 representatives among the 500 Congress people, right? You got to give them either 34 or 35. You can't give them part of a representative. So their actual quota will be one way or the other. All right, enough with all that. Okay. So I'm doing number 2 here. Number 2, and it says, all right, 228 nurses, whatever. They're all the same problem. It doesn't matter if it's nurses and representatives or waters and Congress, whatever. It's all the same thing. You're having representatives. So here we go. So how do we do? And the whole thing is, this one's Hamilton's. Hamilton's. So remember how Hamilton's works? This is the easiest one, right? You start, first off, we need the total here, don't we? Somebody have a calculator? I got a calculator. What's the total there? 875 plus 1,002, 625, 690, 3192. It's the total. So standard divisor is total over seats. So it's 3192 over how many seats? Oh, there it is. 228. 228. 14. Standard divisor is 14. So that means you go back and you divide each of these numbers. You go divide by 14, divide by 14, divide by 14, divide by 14. That makes sense? So just write this out on your 3x5 card for the practice exam today and the real test tomorrow. You can just write out, I'd write out one example of Hamilton, one example of Jefferson. The other ones, there's only 4 methods, right? Hamilton, Jefferson, Adams, and Webster. The presidents came up with these. All right, so you just divide each of these numbers by the divisor. That's why it's called the divisor, right? Divide them each by 14. Let's see what we get. So A, B, C, and D. That's called the standard quota when you divide. So 875 divided by 14, I'm getting 62.5. The next one, 1,002 divided by 14, I'm getting 71.6. The next one, 625 divided by 14, I'm getting 44.6. And the last one, 690 divided by 14, I'm getting 49.3. Okay, now, we do that begins every method, right? All the 4 methods start with that. Find your standard divisor, divide them all. Well, that's not entirely true. We pick different divisors, don't we, for some of the methods. So it's not entirely true. Anyway, what are we supposed to do with Hamilton's? Anybody remember? What do we do with Hamilton's? Remember, we round them all down and give the extra, add them up, see how many extra we need, give the extras to the highest decimals. So round them all down. So I'll just say down. So 62, 71, 44, 4. So down means down. Even like that 0.6 went down. Both 0.6s went down, huh? So there's a difference, right? We talked about yesterday between rounding off. Rounding off is the normal kind of rounding you're used to. When 0.5 goes up, 0.4 goes down. That's called rounding off. When they say round up, they mean up. Even 0.1 goes up. When they say round down, they mean down. Even 0.9 goes down. So I mean everybody down. And then what's the total? Add those up. Let me see. 3, 7, 6. I think it's going to be 6. 226. Is that right? So I'm going to check that. You know what I do to do that quick? I just add up the last digit. All I did, I can't handle that in my head, but I just added 2 and 1. I'm just adding up to ones place. 2 and 1 is 3, and 4 is 7, and 9 is 16. So I know it ends with a 6. And I know it's got to be close, so it's probably 226. That's all I'm doing if you want to save some time. Am I right? Do they all add up exactly that? So you can just add up the ones digit. You know it's close. So 226. So we need 2 more, right? Because it's supposed to be 228. There's 228 nurses that sit on the committee representing all these folks, right? So you need 2 more. So who do you give it to? The 2 highest decimals. That's what Hamilton. Hamilton says, that was Hamilton's method, give extras to the highest decimals. That's what Hamilton said. So and I rounded those. Okay, I'm going to have to go back and see what they were. Oh, the first one was 0.5. Oh, no, it's just those 2. It's just this one, and they have the highest decimals, both the 0.6s, huh? Yeah, there we go. Both the 0.6s. Get an extra one. So this is going to go to 72. This is going to go to, 45. Everybody good with that? So the 4 numbers, this will stay at 62, 70, this goes up to 72, up to 45, and that stays at 49. That'll be 228 reps, and we're done. We gave 2 extras. And that's the answer. 62, 72, 45, 49. That's how we got it. Hamilton's method. Does that make sense? We're deciding how to give the extra reps. It's all about the decimals. The whole chapter is about how you handle the rounding, basically, right? So Hamilton said, just round them all down, add them up, see how many extra you have, 2 extra, and give them to the highest decimals. That sure sounds simple. I don't know why we didn't just stay with that. Just add the extra ones. Is that good? To there? All right, that's the whole question. There's no other part in there. They're harder than Hamilton. All right, so let's do Jefferson. So here's the Jefferson method. You start the same. You add them up. You got to get the total here. What is the total? I have no idea. 1742, 51, 54, 22, 29, 5775. I'm getting 15,000. 15,000. Just add them up total. So what's the standard divisor? It's total over seats. So it's total over seats. So 15,000 divided by 157 doctors. I guess that's my seats. So I'm getting 95.54. That's weird. That's an ugly standard divisor.
Do you round or do you just?
Well, remember good question. For Jefferson, we're going to pick a different one. Remember, we don't stay with the same one. Remember that?
For the standard divisor.
Jefferson, we pick lower.
If it doesn't equal though. I thought because if you
That was Webster's. No, for sure, never equal with Jefferson.
Okay, so
don't even bother with the original divisor. The third one, Webster could, because he rounds off,
right.
So it could come out. But no, because Jefferson's going to round everybody down, you'll always use above to use the standard. You always got to use a new one. Does that make sense? Cole's question was a good one. Is everybody understanding that? Remember the 3 methods? I want to write them on your 3x5 card. So for Jefferson, you pick a lower SD, standard divisor, round down. Right? For Adams, you pick a higher standard divisor, round up. And for Webster, you could use the same or a higher or a lower. Could go any of those, SD, and you round off. So those were the 3 other methods other than Hamilton's. Everybody aware of those? That's what you want to put in your 3x5 card.
So
So Jefferson is pick a lower. So I'm going to take this 95.54, which is the standard divisor, and instead of dividing them all by that, like I would for Hamilton, I'm going to pick some lower number like 94, 93. I don't know. I'm going to guess around 90 maybe. And I'm going to divide them all by some lower number and round them down and add them up and see if they come out to the right total. If not, I'll just keep adjusting. That's where this is a pain. Adams, it's just the opposite. Pick a higher. Like if this was Adams' method, I would pick something higher than 95.54, like 96, 97, maybe 100. I don't know. And divide them all by that number. And round them up. And just keep fooling with it until you get a total 157. If it was Webster, that's the one like Cole was asking about. Sometimes it's actually left the same. Sometimes you use the same, sometimes you use higher, sometimes you use lower SD. It just depends. Try the same at first. That's what we did yesterday and it worked. And then round off, not up or down. Off means 0.5 goes up, 0.4 goes down. Like normal rounding, right, for Webster. But Jefferson and Adams are weird rounding. Jefferson says round down. He means everybody down. Even 0.9999 down. Right? And Adams means everybody up. Even 0.01 up. Right? So those are the three methods. These are a little other than the three other than Hamilton. Hamilton we just did. All right. So what do? I got to pick some lower, since I'm doing Jefferson. Lower SD. How much lower? I don't know. I have no idea. This is where I kind of don't like this method. How about 94? I'm just guessing. If it doesn't work, I'll have to redo it and redo it and redo it until I'm really tired of it. And by works, I mean when we're done, when we divide them all by 94 now and round them down and add them up, they got to come out to the right total. So divide them all by 94. I could have picked 90, 91, 92, 93, 95, anything lower than 95.54, and I don't know how much lower. I'm sort of guessing. Divide them all by 94. Here we go. So 1742 divided by 94, 18.5. The next one, 5154 divided by 94, 54.8. The third one, 2329 divided by 94, 24.7. And the fourth one, 5675 divided by 94, 61.4. We got lucky. This is going to work. I can tell it's going to work. And then round them all down. So 18, even that 54.8, we round it down to 54. 24.7 down to 24. 61.4 down. And what's the total? If you add those up, it's sure enough 157 right on the money. That means we're done. We got it. We got lucky on our first guess. They add up to be the total we need, 157. Now, if they came out too high or too low, we would need to go back and do it again. Remember how that works? How does it work, guys? If it comes out too high, suppose the total would come out 158. What if I'd added them up and it was 158?
You raise your divisor.
You go higher. Yeah, it's counterintuitive. Remember, it's like a teeter-totter, right? So if it's too high, you go higher. Well, maybe that's not teeter-totter. Whatever, forget that. Just it's the same thing. Because you're dividing by the number. If you divide by higher, it brings things down. Remember, it's a divisor you're talking about. So if it's too high, go higher divisor. If it's too low, go lower divisor. And just keep fooling around. But never go higher than the original. Right? 95.54, that's the standard. Jefferson will be below that. So don't go to 96 if you're doing Jefferson. You've got a ceiling already, right? Is that good? You see that? If this was Adams, I would be rounding all those numbers up. 19, 55, 25, 62. I would round them all up if it was Adams, right? Adams is round up. And I would have picked a higher standard divisor to begin with. I wouldn't have done 94. I would have done something like 96 or 97 to begin with. Does that make sense?
What's the Webster method again?
And this, yeah, so then the Webster is you use the same standard divisor, or maybe higher, or maybe lower, and you round off. That's the key to what I like. Webster's a little better. Round off, not up or down. Off, meaning 0.5 goes up, 0.4 goes down. Right? Is that good for those other three? So if we had more time, we could do a lot of things, but we don't have more time. So I'm going to move on to give you a special data table, and then we got to jump into the practice exam. Is that good? Can I flash off that? That'll be on the YouTube. You need it later. Paradox. So I'll put on your 3" by 5" card. You want these. This is kind of like that table we had on the last exam, right? Where we had which things can do which things. So Alabama, it happened in 1882, blah, blah, blah. So I'll just say more seats. Let me just say more seats. More seats, but some state gets less. Right? Like with the kids in the candy bars. All of a sudden, Mom had more candy bars to pass out, one more, and Cindy got less. How could that be? That's called that happened to Alabama in 1882 as they were thinking about doing the seats. And then they backed up and didn't do it. That's why they got rid of Hamilton's method, because Alabama was really mad. So that, can you read that? I'm scribbling.
More seats, but same.
Same. Oh, not same. Some. It looks like same, doesn't it? Some state gets less. So one, like Cindy, one of the kids gets less. One of the states gets less when you're passing out more seats. How could that be? That's called the Alabama paradox. The next one is, what's it called? The new states paradox. These are paradoxes, meaning they're not what we'd expect. They're surprises. Okay, so what is that one? The new states. The addition of a new state with its fair share of seats can cause shit. New state joins with its fair share of seats. Other states switch numbers. That's surprising. Shouldn't happen. What I'm talking about, that happened in history again in 1907. Oklahoma joined the Union. So basically it's like, as the United States was growing and more states were coming in, they were making the House of Reps grow. And so as it grew, they tried to bring in new states and also increase the House of Reps, so they weren't taking any from anybody. But every now and then they would do that, and it would end up taking some from other people. Even though they gave the new state their right number, it would shift between two of the old states. That make sense? So that'd be like the kids. That'd be like if a new kid, and I think that question will go on and say that. Yeah, let's go back. If I go back to, well, I'll do it in a minute. I'll go back in a minute. Let me just give you the third one. What's the third one? Population. I forgot that one. There's a population paradox. Population. It's the last one. Paradox. These are the three weird things that can happen. And that is what? State with a positive population growth can lose a seat to another state with a smaller. Okay. State growing. State with a positive growth can lose it. State growing can lose a seat to another state growing slower, which is weird. So year by year, the states would grow. It's California, obviously, is growing the biggest, right? People moved out west. And so as California grew in population, we got more and more and more of the representatives. But sometimes what can happen, and these are all from Hamilton. These are all bad things that and I'll write that out in a minute, that Hamilton's method can do. You'll have one state growing faster than another, but the slower growing state will actually steal a representative with the calculation of Hamilton's method. All right, everybody got those down? I'll go back and I'll show you how we see those. In fact, actually, let me just give you a quick table. Everybody got that down? Can I flash over? So put that in your 3x5 card. Come over here. Now, here's especially what you want in your 3x5 card. I'm going to give the quota rule. Make a little chart for you here. And Alabama, the Alabama paradox, the population paradox, and what was the third one? New states. The new states paradox. All right. And bias in favor of. These methods are biased a little bit. And I'll show you how they are. Oh, I don't want that. So we got Hamilton, Jefferson, Adams, Webster. All right. Can it? Oh, wait. Oh, and then at the bottom I'll put the quota rule, yeah. Quota rule. That's important too. Okay, so here we go. Yes. 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 Large states. And the other ones are, all the other ones are no in the top sections. Except for Webster. Webster is not biased, neutral. And then the quota rules, none, upper quota violation, lower quota violation, upper and lower quota violation. All right, there's the big, so that's like the big chart we had on the last exam, right? You need that on your 3x5 card because there's going to be like 3 or 4, maybe 5, probably 3 or 4 questions on the practice exam today, real exam tomorrow that directly are answered by that table. Because that table shows you how the different methods play out, how they work. I forgot about the quota rule violation. I'm going to need to explain that one. But first off, let me explain what it does say. So, the 3 paradoxes we just talked about, right? The Alabama, the population, and the new states. Notice that Hamilton can do those bad things. But the Jefferson, Adams, and Webster will never do those weird, bad things. That's why they started changing methods. Because Hamilton could do the weird, they just discovered it. They were about to, Alabama was, they got some extra representatives, and like with the candy bars with the kids, right? There's 12 candy bars, not 11. All of a sudden, Cindy's losing one. How could she get 1 when there's 11 candy bars, and then she loses it when there's more, when there's 12? How could that be fair, right? She didn't go do any more homework. Nobody changed their minutes of homework. And we've got more candy bars, not less. How could Cindy get less? How can that be fair? Well, that's how Alabama felt. We got more. The House of Representatives grew, and it caused Alabama to lose one. They're like, wait a minute, folks. There's somebody doing something bad. If there's more representatives on the House now, and we didn't lose any people in population, how is it we're losing a representative to your bogus system? So that's when they were mad at the Hamilton system. So that's the Alabama paradox. Population is when, I wrote it out a minute ago, when the population of one state grows faster than the other, the slower growing state gets the extra rep, steals one. And the new states is when a new state comes in, it'll cause shift among other states sometimes. Hamilton can do all those bad things. The other methods do not. They never will. They've been mathematically proven to never do that. Okay, well then now, but here's part of the problem. Come on down, bias. The methods have been proven that Hamilton and Jefferson tend to favor larger states. They'll give more representatives to larger states. California, for example, we would be favored by the Hamilton and the Jefferson. Adams favors small states. Webster is neutral. There's no bias in that. Quota rule. Let me explain. You guys write it down. No quota rule violation, upper, lower, both for Webster. What is a quota rule violation? Let's go back. Well, you know what? Let's just go back. We'll see it all with the candy bars. Let's make it up with the candy bars. We've got the 11 candy bars, right? We got, what do we got? Cindy. Who are those kids? Where are they? Cindy, Bob, Mary, 1, 2, 8. Cindy, Bob, Mary, 1, 2, 8. Cindy, Bob, Mary, 1, 2, 8. So that's how we broke up the candy bars with Hamilton, right? And then we went up to 12 candy bars. And she lost one, and I don't know, did Mary get it? Something like that? Probably they each got one. Is that what happened? Let me go back. Yeah, 039. Yeah. So that is the Alabama paradox, right? When that happens, right? You got more candy bars, but Cindy gets less. How could that be? Not fair. That's Alabama. Now, what about, let's do the, what were the other ones? The new states. What if a new kid, so let me do part B. That's all, let's say part A. Part B, some new kid shows up. She forgot about her fourth child, maybe. All right, I'm stretching it here, but whatever. So there's this other kid. She all of a sudden forgot, oh yeah, Dale, I forgot he did some homework too. So let's add Dale to the mix. We got to go back. Okay, give me back the 12, 11 candy bars, whatever. Let's go back to the 11. Give me back the 11 candy bars, and we'll bring in Dale. We know she adds up Dale's minutes, and she says, hey, Dale should get 3. Dale should get 3 candy bars. So the mom says, look, I don't want to take any candy bars from anybody. So I'll go to the store. I'll buy 3 more candy bars because I already calculated that's what Dale should get. Dale should get 3 candy bars, based on the amount of homework he did. So she gives Dale, she goes buys 3 more candy bars, gives Dale 3 candy bars, does the whole Hamilton method thing again, and something like this happens. Do you see how these two swapped? Eve and Mary stayed the same. See how they swapped in the new calculation? Cindy and Bob would be like, well, Cindy'd be happy. But Bob would not be happy. Bob would be like, what? Why would we trade just because you got a new kid and you bought the candy bars for that new kid? You said the new kid gets 3, you bought 3, you gave them to the new kid. Why are we trading? Well, Hamilton's method can do that. When you bring in a new kid, new state, that can happen. That's called the new states paradox. You bring in a new kid, it can actually cause a shift among 2 of the old ones. All right, finally, part C. So that was A, B, now over here, part C. The population. What if going back to the kids, Cindy, Bob, Mary, she says, all right, kids, go back and do some more. I'll give you 1 more week. Go do some more homework. And they do a bunch more homework. One more day, study hard, and then I'm going to do the candy bars. 1 more day. Give me 1 more day to catch up in case you didn't realize. So they go back, do a bunch of homework, and Cindy, let's say, does more. Well, she does a bunch more, and Bob only does a little more, right? Well, it turns out Cindy might actually lose one. That can happen. They both did more. Both Bob and Cindy did more. Cindy did a bunch more. Bob only did a little more. And yet Cindy loses one to Bob? That's called the population paradox. A slower growing state can steal one from a faster growing state, which doesn't seem fair. All those can happen under Hamilton's method. That's why people got mad at Hamilton's method when the United States was forming their House of Representatives, because it could do those weird things. Now, the other methods, Jefferson, Adam, Webster's, won't do those things. They won't do those bad things. But they can do something, in my opinion, even worse. They can violate upper and lower quotas. Let me show you what that is. You guys all got that copy down? This is taking way longer than I thought. Look at that time. See, I live in a dream world, don't I? All right, so story of my life there. So, all right, you ready? So I'm going to go to a new page. So, final thing. Quota violations. Yes, Hamilton's method does those other bad things. These are all done by Hamilton's method. Hamilton's method can do all those bad things. That's why they ditched it and went to Jefferson, Adams, and Webster. But Jefferson, Adams, and Webster can violate quotas that Hamilton never would. So let me show you what that is. So quota violations, what are they? Remember the standard quota when you divide them all? Let's go back to the Cindy thing. Cindy, Bob, Mary, right? Let's say their standard quota. Standard quota. Suppose, what were the numbers? I forget them. 1, 2, 8. Okay, let's suppose Cindy needed 1.2, 2, so 2.3, and 8.4. Right? Let's suppose those were their standard quotas. So we rounded that to 1, rounded that to 2, and rounded that to 8, and that's what they got, right? Standard quotas. But what could happen is, what if you take the 1.2, the 2.3, and the 8.4, and you round this to 3? What if you round that to 3? It doesn't round to 3. No way. Well, that's called an upper quota violation. Right? The highest, 1.2, the highest it should ever go, even if you round everybody up, is 2. Right? You with me on that? The highest it should ever go is 2, and the lowest it should ever go is 1. It's between 1 and 2, right? 1.2, $1.20, between $1 and $2. So the highest you go is 2, the lowest you go is 1. But it turns out, Jefferson, Adams, Webster, they could kick it up to 3. Well, not all of them. Which ones can do upper quotas? Jefferson and Webster could kick it up to 3. That's an upper quota violation. Now, let's do Bob. Bob is 2.3, so he should either end up 2 candy bars or 3 candy bars, right? He's between 2 and 3. What if Bob only gets 1? There's no way Bob should go that low. He really deserves 2.3, but we don't want to give him part of a candy bar. So we're either going to give him 2 candy bars or 3 candy bars. What if our little method ends up giving him only 1? That's called a lower quota, because he went below the bottom. That'd be a lower quota violation. Does that make sense? When it goes below rounding down or above rounding up, those are called quota violations. Right? So that's what they mean. And those other methods can all do that. That's the bad thing about Jefferson, Adams, and Webster. They can round above or round below where you would ever round. They can violate the quotas. So none of the methods is perfect, and that's the end of the story. There's no perfect method. They've argued, or they actually decided finally, a bunch of court cases. Today we use, it's kind of like Webster's, it's called something or other. You can type it into Google, find, U.S. House of Representatives Apportionment Method, if you're really interested. I probably have the name here somewhere. Oh yeah, there might be a name on the test. Let me give it to you. That's right, I put that on the test sometimes. I better tell that to you then, huh? Sorry. It's not funny. All right. What's it called? I don't remember. What is it called? What is it called? I don't know. I don't know. It's kind of, Huntington Hill. There it is. Huntington Hill. So today, so after this was all done, here's what we use. There's 435 reps in the House. That's set fixed. They've decided it's not moving. They made a law. They passed a law that it won't move. 435, right? Isn't that? Do I have that number right? Is that what it is? You got it on the Google or something?
Representatives?
Yeah, 435. Thank you. And we used the Huntington Hill method. So we actually don't use any of these, Adams, Webster's. It's like Webster's. It's a similar version to Webster's with a couple small fixes. That's what we ended up using. It's the law now that they will use Huntington Hill method to pass out the House of Representatives. People care a lot about all this because it matters on vote counts and all that. So that's what we use today, the Huntington Hill method, which I'm not going to show you. We don't have time for that. I don't even know it, to tell you the truth. I just know it's something like Webster's. Basically. You can read all about it, I'm sure, on Google. But you can do it in your spare time this evening. Right? All right. We good with all that? Does that make sense? That's chapter 4, chapter 3. We've got them all. It's all the information you need. Any questions on all that? You ready for this practice exam? Sentence 1240. Time to take it. So why don't we do it? Because I want to go over it well with you. We've already done questions, so we already do have kind of heads up. We've already done 1 through 4. So you can skip those, right? We already did them together and in the quiz time. So we did 1 through 4. So skip on to number 5. Do what you can. We better stop in about a half an hour. Yeah, because I need to go over this with you. So let's stop in half an hour. Do what you can for half an hour. Then we're going to stop and I'm going to go over with you. Wait, am I double? Can I get some people other ones? I'm going to run out. Some people already have them? No? I'm thinking right. Who else? I gave somebody one, didn't I, already? I'm out now, and I need one more. Who got 2? No more, remember Rome? Did I give you 2? No, just 1? Practice exam? Or maybe I just can this one, I guess. There's another one. Oh yeah, feel free. Yeah, feel free. Yeah, there's old tests up here. You can grab one of the yellow blue tests too if you want. Which one do you want? You're going to get one? I do. Oh, genuine? There you go. Cool. Yeah, so Scantron's like last time? Yeah. Scantron, I'll grade it for you real quick. We already did the first 4. What were they? Somebody have those answers? Or here, I'll just give you the answers for the first 4. If I can find them. Go. Pen vanished. Oh, there it is. Oh, I'm sorry, guys. One other small thing. Really quick. Belinsky and Young. Impossibility. Possibility theorem. 1980. So you might be asked about that. It was proven in 1980 that there could not exist any method of apportioning that doesn't break one of our senses of fairness. Just like Arrow's impossibility theorem on the last stuff. Remember how Arrow came along in whatever it was, 1970 something, and proved that there never could be a voting method that doesn't do something unfair? This has also been proven, so the search is over. It's been proven that there never could be. Not just that they haven't found it yet, but it couldn't exist. There could not mathematically exist an apportionment method that is always fair in all situations. Every way of apportioning seats will do one of those bad things. One of the quota violations or one of the new states or Alabama or population. It will do. 1980 is pretty recent. That's fairly recent math, you know. A lot of math was proven 200 years ago, but this is pretty modern. 1980, that was proven by Belinsky and Young, so you call it the impossibility theorem. You might be asked, write that down. That could be asked.